let's get started. So, hi everybody. Thank you for coming to my talk today. I'm going to be talking on persistent storage for Kubernetes in production. Which solution and why? So, my name is Cheryl. I'm on Twitter at Cheryl. I run product and DevOps at a startup in London called StorageOS. We do persistent storage for containers. I'm an ex-Google software engineer, and I'm a CNCF ambassador. I run the Cloud Native London meetup group. So in today's talk, I want to answer the following questions. Why is state so tricky in the first place? How do I compare the different storage options that are available to me? And then what do I need to know about using storage with Kubernetes? Actually, quick poll before I start. So who is new or beginner to the idea of containers in Kubernetes? Couple of people, OK. Who's been running it in production for a year, 2 years? OK, maybe half. Who has been running it in production for more than that, 3 to 5, whatever years? OK, nobody. 1 or 2 people. OK. I asked because I come from a different angle in that at Google, I've been using containers since 2010. So I don't really remember a time before containers. Like, to me, everything's always been containerized. So different point of view. OK, one thing I don't want to talk about is, should I be using a database or a key value store or something else for my app? I'm just going to talk about the storage layer. OK, why is state so tricky? Why do I even need storage? Because most people here probably know that containers are supposed to be immutable and they're supposed to be stateless, which is good because you get some nice abstractions if you assume that everything is stateless. Unfortunately, there is no such thing as a stateless application or a stateless architecture. If you're doing something useful, you have to store data somewhere, which means you have to make a decision about the storage. OK, first challenge, no storage pets. So this is the pet versus cattle analogy for servers. So you don't want to treat your servers like pets that you name and you lovingly look after them, and when they fall over, you have to nurse it back to health. Instead, you treat them like cattle, so you number them, and when they fall over, then you take it out back, you shoot it, and you slot in a new one. So you want to avoid treating your storage like pets and having special servers that are your storage servers, because now you're tied to looking after those. Second challenge, data needs to follow. So hopefully your containers are small and lightweight, and you expect to be able to run them and have Kubernetes spin them up and down anywhere. Your data needs to follow the containers, no matter where it goes. You want to avoid having to map specific containers to specific hosts because of the storage, because then you lose the portability and the mobility of the containers. Third challenge is humans are fallible. So you should avoid having humans run through playbooks, because it's just a recipe for eventual disaster. 22% of data center outages are caused just by human error. So you need to have everything automated as much as possible. When nodes go down, you want the storage to just fail over seamlessly. You don't need to be worrying about that. OK, how do I compare storage? So Ihor earlier showed us the CNCF landscape. If you zoom in just onto the storage section, this is a little bit out of date. You probably have 30 options here already. So then you go look at all the cloud providers, and they all have many different options. So how do we even compare what the storage options are out there? I'm going to present a framework. This framework is the 8 principles of cloud-native storage. So this is an attempt to talk about what cloud-native storage should look like before we get into the details of choosing what you need. OK, what do I mean by cloud-native? So cloud-native means it should be horizontally scalable. You should be able to add resources by adding nodes to a cluster instead of making each node individually bigger. It needs to have no single point of failure, And if there is a failure, then the system needs to be resilient and self-healing, so it fixes itself. Minimal operator overhead. So I said before, everything should be driven as much through APIs and as automated as possible. And then it needs to be decoupled from the underlying platform, which is particularly difficult for storage. You want your storage to work exactly the same way, whether you're running on-prem, in AWS, Google Cloud, Azure, anything. So let's go through the 8 principles. So first principle is storage should not be defined by the host that it's running on or the node that it's running on. What matters is your containers, and therefore the storage needs to be oriented around what the container needs, not what an individual node needs. Second principle is storage needs to be platform agnostic. It needs to be able to run anywhere. So if you want to be able to run it over multiple platforms, you want to be declaring the storage through your YAML files, through all the, just as you would declare other resources like CPU and RAM, you want your storage to be declared side by side. And in order to declare it side by side, the storage has to be completely automated, completely API driven. You need to be able to provision storage, manage it, consume it, all through APIs. Fifth principle, when you consume things through APIs, you have to care about who is accessing it and how. So you want to have RBAC so that your storage is not completely open to the world, and you want your data to be encrypted as well. Sixth principle, just as containers have made compute and applications agile, storage and data should be agile. You should be able to move data around from location to location, from region to region, from data center to data center, without it interrupting service. And then the purpose of all of this is because we want performance and we want it to be consistently available. All of storage boils down to give me data and make sure it's always there when I need it. That's all that a developer cares about. Okay, so what do I need to think about when using storage with Kubernetes? So for the people who are sort of new to the idea of Kubernetes, I'll do a very quick introduction. So it's an open source container orchestration platform, originally developed by Google, now open to the community. It's one of the fastest moving projects in open source, and it's been called the Linux of the cloud because it's becoming the standard for how to run containers and applications, and it's an abstraction layer for infrastructure. So if you don't know Kubernetes, you just need to know 2 concepts. So one is declarative infrastructure. So in this case, you can say, always run my application packaged as a container or pod with 4 replicas. The second concept is a control loop. So Kubernetes will read in the specs that you've given it. It will measure the difference between what is actually happening and what you've asked for, and then it will issue commands to try and get the system closer to what you've requested. And then it will do that in a while loop, round and round and round, always trying to get closer to the requested spec. So architecturally, there is a master. This is a 2-node Kubernetes cluster, 2 worker nodes. And in this case, there's 4 running on overall. If one of the pods dies, then Kubernetes will restart it, so you get to 4. If there's 5 running, then Kubernetes will kill 1 and get back to 4 as well. Okay, that's my extremely quick intro to Kubernetes. So let's look at the storage model for Kubernetes. So the base level of abstraction of a piece of storage is a persistent volume in Kubernetes. Persistent volume has a size, it might be 10 gigabytes, and it's backed by some actual piece of storage. And in the Kubernetes world, an administrator can create a bunch of these persistent volumes, or PVs, place them into a pool. And then a developer can write a persistent volume claim, which is a request for a certain amount of storage, and Kubernetes will match up the claim to one of the available persistent volumes, and then the developer references the claim in the pod, and that way that piece of storage is now associated with that container. Okay, so far so good. But the problem with this model is this requires the administrator to create those persistent volumes in advance, which is not what we want, because we want things to be in demand. We don't ask an administrator to create a certain amount of CPUs for us. So how does it look for storage? Okay, so this is called dynamic provisioning. So instead of creating persistent volumes, now an administrator creates storage classes, and these describe a profile of storage. So you might have fast storage that's available on SSDs, and then standard storage, which is available from ordinary hard drives. A developer will write the persistent volume claim as before, and this time Kubernetes will only create the persistent volume and actually associate it with the pod once it's been requested. So that is dynamic provisioning in Kubernetes. Okay, let's go through a worked example. So meet Jane. She's a DevOps engineer at a company. She wants to follow those 8 principles of cloud-native storage, and she understands the model of Kubernetes. Her job is to migrate some client WordPress websites into the new Kubernetes architecture. What storage should she choose? Okay, so first question to ask, what is my use case? Because so far I've talked about storage as if storage is one thing and there's only one thing you ever need storage for, which is not true. So there's many different use cases for storage. Common ones are you need somewhere to store your application binaries, you need to store your application data, you need to store configuration files, and usually your data needs to be backed up somewhere. So what does this imply for performance requirements? Binaries are ephemeral, so you don't need to worry about persistent storage for binaries. Application data is where you care about latency, and throughput, and availability. Configuration files need to be shared across multiple pods, multiple instances. And then for backup, you're trading off availability for cost efficiency, and you might want to be backing up to the cloud. Third question to ask yourself, how are my developers going to be accessing this storage? So a quick storage 101 as well. So there's 3 kinds of storage. There's block, file, and object store. So block storage is a fixed amount, access a fixed amount of memory or storage at a particular location. So it's very rigid, but you don't usually access that directly. But it's particularly good for databases. So files are an abstraction of storage that sits in a hierarchy. It's probably POSIX compliant, so it has read-write executable permissions. And yeah, it sits in folders. And then there's objects, which are completely unstructured. You just throw it into a bucket, and it's better for big data use cases. Fourth question, how is that storage going to be deployed and managed? So there's many different ways that your storage system can interact with Kubernetes. So Kubernetes can access it directly. It can access it through one of the plugins, through the frameworks and tools that are available. You can use one of the interfaces. So container storage interface is new or coming up, and I'll talk a little bit about that later. But each of these means you have to manage the storage in a slightly different method. Okay, so that was it, 4 questions. So what's my use case? What does it imply for my performance? Anyone remember the third one? How are developers going to access it? And then how do I want to be deploying and managing it? Okay, back to Jane and her needs. So she has multiple use cases. So the application data is stored in Postgres. That database has a location and it has credentials that need to be discovered by the pods. She needs to back up the database and the websites. And then WordPress lets you upload videos and images and large blobs of data as well. So let's go through these and see how she would use them with Kubernetes. So let's start with where the database is located. and the credentials. So this is a configuration use file, which means it needs to be shared. Kubernetes already has primitives for this kind of data. So you can provide secrets, or you can use secrets to store passwords or other confidential data. You can use config map. All of this is integrated tightly into Kubernetes already. The second one, user uploaded media. So these are the images and videos that her users will upload using WordPress. So this is a shared media use case. So this is large blobs of data, and multiple pods need to access the data. So this is actually quite a good use case for a shared file system, or possibly an object store if the application can handle object storage. So she's on cloud. There's managed NFS options like EFS. Anyone using EFS? Out of curiosity, a couple of people. Any thoughts on how it's worked? Good, bad? Good? Good? Okay, cool. So yeah, managed NFS, like EFS options, are pretty simple. They can have performance issues, but other than that, they're quite good for this use case. If she's running it on-prem, then there's distributed file systems. So Cluster FS is quite a popular solution for this. I put not NFS. So who's using NFS at the moment? Okay, like 24 people. So tell me about NFS. So why did you laugh? Mm-hmm. Yeah. Okay. I should have given you the cube to say that, but basically it was why. So you don't want to run NFS on top of a SAN because then you're duplicating the replication. The other problem with NFS is usually NFS becomes a bottleneck, a single point of failure in your system. So we said before, no storage pets, right? Whatever your NFS is running is like your definition of a storage pet. Now, NFS also has issues with file locking and other things. But if you're thinking cloud native, then NFS is not the best option out there. Not really built for these kind of architectures. Okay, backing up the database and the websites. So backup and archival is reasonably well solved as a problem. So you care about the cost, and you care about being able to snapshot the data, but you're not accessing it regularly, so availability is not as important as durability. So again, object store is a very good option for this. So manage object stores. So anybody using S3 for this? A couple of people? Yeah, okay. And then there's long-term cold storage options as well that are all the cloud providers provide long-term cold storage. And then on-prem, there's object stores that you can run on-prem as well, like Minio. And I've put a not a NAS for similar reasons in that you don't want that storage pet again. So that's quite similar conceptually to the NFS reasoning. Okay, now we get to the Postgres database. This is a transactional database, so this is the one where you care most about availability and low latency. And you also care about deterministic performance. So it's not necessarily the case that it has to be the fastest possible, but you want to be able to rely on the performance being stable. You don't want a long tail of like every once in a while one query takes 20 minutes to return. So it's more important that it's deterministic. How are the developers going to access it? They're probably going to be using a database connector, although as we talked about before, databases run best on, or fastest on pure block storage. And then, okay, how are we going to deploy and manage it? So cloud options. So there's cloud volumes, like EBS. So anybody using EBS or Google Persistent Disk or whatever other, what's the Azure one called? Anyone? Okay, nobody knows. Okay, cool, a handful of people. So these are the default way that a cloud provider will give you storage through the storage class. I put watch out for attached detached times here, because if one of your nodes goes down, then detaching and reattaching that volume to a different node can be somewhere between 45 seconds and an hour. So if you're expecting to be able to move your pods quickly from node to node, then they may not be a good option for you. If you're working in a regulatory environment, then you need to worry about compliance. Or there's managed database, so RDS and the like. I actually quite like RDS. I think it's a really good choice, as long as you know what your standard is, and you don't need some specific version of a very specific database with customizations. As long as you can take the defaults that they give you, then managed database is quite a good idea. Okay, what about on-prem? I put software-defined storage here. And maybe unsurprisingly, I'm going to use StorageOS as an example, because it is a software-defined storage platform. So this is a diagram of how StorageOS works, but there's similar ones out there. So it runs as one container on each host, and it finds all the block storage attached to each node and aggregates it into a virtual storage pool across the whole cluster. And then from this virtual storage pool, you create virtual volumes and mount those two containers, instead of using volumes that are on a specific host. So I think I'm going to be a little bit out of time to actually run this demo, because I want to give a couple of minutes for questions. So I'm going to actually instead talk about one concept of StorageOS, and then that is the end of my StorageOS pitch. Okay, I just want to describe how StorageOS actually works under the hood. So this is a 5-node cluster. StorageOS is running on each of these. And the architecture is of a master with distributed replicas. So I've got a volume D, which is on node 1. And you can request between 0 and 5 replicas. And it creates 0 to 5 replicas across 0 to 5 nodes. So in this case, I've got 2 replicas running on 2 random nodes. Data comes in and is synchronously replicated to each of the replicas on node 3 and node 5. When they act back, that's marked as a success, and then that write has succeeded. So what makes this interesting? So if the node 1 goes down, then StorageOS can just switch one of nodes of D2 or D3 to become the new master. So the failover time is instantaneous, and then you can also move pods around, and they can access volumes on any node. So that means the pods can move around, and the nodes can go up and down. You can scale it by adding nodes. And that is just how high availability works. That's the end of my StorageOS pitch. And in fact, the end of my slides. So quick recap of what we've talked about today. So the 8 principles of storage, of cloud-native storage, are make sure it's application-centric, it's agnostic to the platform underneath, and then all the other ones around being able to declare it, compose it, use it through APIs. If you are trying to pick a storage solution for your applications, your system, you need to ask yourself, what is the use case? What does that mean for the performance requirements? How is it going to be accessed? And then where is it going to be deployed and managed? And from those questions, you can pick different storage options for your different use cases. CSI, I said before, Container Storage Interface, it's currently in beta, and from now on, it's probably going to be the way that you run storage in Kubernetes. So rather than using a particular, depending on a storage vendor like AWS or Google Cloud or the way that they do their APIs or StorageOS, they'll all provide a CSI. They'll write to the container storage interface, and then that means that you as a DevOps or sysadmin can move from different storage vendors more easily. This was the demo that I was going to do. It's available in the browser. It gives you a cluster that you can type commands into and try it without having to install stuff. So if you want to try it yourself after this, then it's at demo.storageos.cloud. There's also a quick start guide for StorageOS. So thank you. My slides are on my website at oishow.com. Before I go into questions, I'm going to get a photo for the purposes of Twitter. So I want you to all wave. Bit more enthusiasm, please. Woo! Awesome. Okay, excellent. Thank you, everybody. With that, I open the floor to questions. Oops. Go back a bit more.
It hit. So you said that replication is synchronous. Does that mean that the throughput of the storage is limited to the slowest node?
There are different options you can use. So we don't have fully asynchronous replication yet. So for the most part, it is limited by the speed. Actually, it's more limited by the geographical distance. So if the cluster was very geographically distributed, then yeah, you won't get the best performance out of it.
Thank you.
In front of you.
So I guess you're using Raft consensus or one of these common algorithms for replicating data?
Conveniently, I have some bonus slides. So this is the actual architecture of it inside. It's a bit hard to read. So we have we actually store the configuration of the cluster using etcd, using a key value store. And then we have our own scheduler to determine where the masters and replicas are placed. So you can balance the throughput on each node, which is Raft-based, yes. Any more questions? Okay, cool. Thank you very much.